So hope everyone is able to see the screen all right. Yeah. So
Yes,
hi
yes.
everyone. I'm Vikas Garg. As you just heard from Kari, I'm a professor at Aalto University in Department of Computer Science. I'm also a professor with FCAI, and I'm co-founder and chief scientist at EAA Limited, which is a deep tech solutions provider company dealing with especially in quantum and AI technologies and focusing on sectors such as energy, EV, telecom, and IoT. So today I'll be speaking about renewable energy integration into intelligent systems. So I was just looking up one question in the chat window. Someone was saying that, is AI going to make us mentally lazy in some sense, in that that we are going away from analytical solutions. So hopefully this will allay some of those concerns. Yeah, so smart grids are becoming increasingly complex. We have all kinds of sources, the conventional sources, the non-renewable ones, and then the renewable sources such as the wind power, the solar, and all this. And there are all these interesting questions that are arising with respect to the generation, transmission, distribution, and then this integration of electrical vehicles and all this as part of this smart grid. So suffices to say that our systems are becoming really complex. Now let's see what are the key goals. So essentially what we want is efficient generation and energy management. So there are questions, for example, both on supply side and the demand side, regarding, for example, how do you do generator scheduling when you have these multiple generators, some of which, like the conventional sources, which which you could rely on in terms of how much energy would be produced, for example, if you use a certain amount of oil or gas. On the other hand, the renewable sources such as the wind or the solar, they are intermittent power sources in the sense that they heavily rely on, for example, things like weather conditions. And so they are more difficult to integrate in some ways. And as you see, like for example, in this outline of what a modern smart grid may look like, you have all these kinds of data needs, such as the need for data center energy management system, home energy management system, then building energy management system, and even further community energy management systems. So for the purpose of this talk, I'll keep the agenda slightly more concise. So we will not go into, for example, the integration of electrical vehicles and IoT and telecom. We will focus strictly on power. How could we specifically leverage these estimates or predictions about, or the forecasts about your renewable sources of energy? For example, how is sunlight going to be in a particular area, or what's going to be the wind speed in say a couple of hours? So how do you make the most of these estimates, which are not precise, but nonetheless they convey some information to you? So is there some value in exploring those, and could AI help us in accomplishing our goals? So that's how we will. That's what the agenda for today is going to be. So there are lots. So let me first just briefly mention that there are tons of opportunities and challenges when we talk about integrating the renewable sources into the modern smart grids. First of all, there are certainly some benefits because of which it's becoming such an important topic. First of all, integrating renewable power is in some ways vital for reducing cost as well as reducing the carbon footprint. There are, however, certain challenges. As I mentioned, that renewable power is intermittent. So for example, if your wind speed is not sufficient, then we may not generate power. Likewise for the solar energy, depending on the duration and brightness of the sunlight that you get. So these are not the factors that are certainly under human control, but could we do something with those? And as I mentioned, that often we have forecasts available, for example, from the weather department. These forecasts may not be precise, especially when we deal with the something like wind speeds over a slightly longer horizon, but certainly there is some value in using these forecasts. And there are challenges that essentially are spread across the spectrum. For example, extracting value from these renewable sources requires efficient management of generators. How do you schedule your generators? Then storage, because for renewable power especially, you need to store store the energy, since it's intermittent. And then how do you manage your loads? And suffices to say that many of these questions can be posed as dynamic optimization problems. So you get certain predictions regarding your wind speed, for example, and then you want to take that into account and formulate some meaningful optimization problems that hopefully can be phrased in terms of AI, and we can do something with it. So I will focus specifically on one use case, and this is essentially from a household perspective, that you are a user and you would like to manage your storage. So we will assume that you have some battery resource, and also let me try to you see a formulation here. So let me try to motivate this formulation. So here what you see is dt. Dt is the demand at time t. So this is the demand of that household that must be satisfied. Now there is a component which is provided by the renewable energy. This is what you see here as RT. Now ET is the charge that you are essentially taking out of your battery, which is your secondary storage. And then PT is the amount that you are purchasing essentially from the grid. So your demand is essentially met by three components: the renewable energy that you are able to derive, the energy or the power from the battery storage that you have at your disposal, and also the energy that you can buy, for example, from the spot market. Now, clearly, for meeting this demand, if this demand is met, the user derives certain value, and so certain utility to speak of. And this utility you see here denoted by UT. Now there are various kinds of utility functions that have been that are quite natural. For example, one way is that you have a minimum level threshold DT, capital DT, which you want to be satisfied. So you want at least that much budget of power available with you. And if you don't meet that, then you essentially don't derive any utility. But if anything greater than that, then there is a certain amount that you derive. So there are other kinds of utility functions also possible. Typically, people assume some kind of concavity or other kinds of tractable assumptions. For our purpose, we don't need to make any assumptions. So you could have any choice of utility functions, any worst case choice, and the results and everything that I speak of would hold very generically. Now you also see ET. So as I said, ET is the charge that you draw from your battery at time t. Now there are certain constraints. For example, you cannot just charge or discharge your battery instantly. And so here BCH is the maximum charge or discharge that you can do to your battery in single slot. And here I am restricting it to say 0. That's saying that you are only withdrawing essentially the charge from the battery. But more generally, you could also replace the lower bound by minus BCH here, which essentially would mean that sometimes you would also be charging the battery that you have. And now the state of the battery, once you B here is the T is here the state of your battery at time t. And so like when you withdraw some charge ET from this battery, it reduces. And likewise, if you add it, if you charge, it will be added. So this is what we are trying to do. So essentially, we are trying to maximize the welfare, which is essentially the utility that you drive at each time step, minus the cost of purchasing the power from the grid. So you're buying PT units, each unit costs CT. So PT CT is the total amount, total cost that your total expenses for buying PT units at time t. So what we are interested here is in maximizing the overall welfare across the time horizon t. So I hope the setup is clear. And what we want to do here, as you see, the variables that we are trying to optimize over are P1 through PT, which is how much units of electricity are you going to purchase at each time, each time, and then even ET is how much energy you are actually withdrawing from your battery. So we are trying to optimize for what you take from the battery versus what you buy from the grid. So we follow a slightly, slightly unique approach here, a new approach, which is essentially to discount the future welfare estimates. So just to be clear, our objective here is what I just mentioned, that we want the total undiscounted welfare across time horizon T. We want to maximize that. But what we will do is we will follow a different strategy where essentially we will discount the future welfare estimate. So here gamma that you see that we have used a discount factor, in front of the welfare, instantaneous welfare for each time step, and we are raising it to a power. So as you look more into the future, and here L is essentially abstracting the forecast that you have available. So for example, you could have forecasts available for next 3 hours or 4 hours, in which case your L would be 3 or 4. And so what we are essentially doing is we are weighting because gamma here is a parameter which is between 0 and 1. So essentially we are placing more value on the instantaneous estimates compared to those for the longer term. And we solve this problem in an online fashion. So at each time step, we will compute this path essentially of at each time T, we will solve for or estimate a path T to T plus L, which will essentially tell us which is the most optimal path, estimated path with respect to this discounted strategy. And so this is the strategy that we will follow. Now, this problem can be reduced very nicely to a reinforcement learning problem where you are working with the MDPs. And here we only have the deterministic transitions because the problem can simply be cast in terms of the battery state DT. You don't really need to take into account P1, PT, and ET because demand is just a function of a renewable component, the battery component, and the amounts that you purchase. And so here because ET just determines what your BT plus 1 would be. So you could just essentially cast the problem in this setting simply in terms of BT plus 1. The power that you buy at time T is local. It can be just solved this. So we can do essentially cast it in terms of a reward formulation with for an underlying Markov decision process. And let me just convey briefly in 1 minute, like what the essential intuition here is. So here, each row, think of it as a state and each column as a time. Let's say that there was an optimal offline path. So I showed you the initial problem that we wanted to solve for, the undiscounted problem across all the time horizon. Now, suppose there is an optimal solution for that. Suppose you knew everything about the system, all the estimates were available to you beforehand, before you started the problem. Then there was some path that this the offline optimal algorithm would have taken. If suppose there were no ramping constraints in the sense that you could arbitrarily charge or discharge the battery to its maximum limit at any time step, then one possible strategy for us would have been to just jump to lose possibly, like the reward in the current step and follow the optimal offline policy in the next step. It could be anywhere because we are doing an optimization over all paths. So optimal path is also one of those paths. So this is already covered. And so this is how we essentially can resolve these problems multiple times and at each time step in a very efficient manner and then derive benefit from it. So we cannot be doing too worse compared to the optimal path, at least in the discounted setting. Now, as I said, that you cannot arbitrarily charge and discharge in each time unit. So there are certain constraints, ramping constraints. So for example, you could only charge to half the level or discharge by half the maximum level. In that case, you will need to skip more steps. And so your performance would, of course, of course degrade. So that's the essential idea, and it can be shown that this performs really well. So you get theoretically optimal guarantees, which is, and even for small look ahead, you are almost optimal. So even with forecasts, limited forecasts, you can do a great job. And I'm not mentioning here like the more technical aspects of it, but even if these forecasts are uncertain, as I mentioned, you can still do possibly you can still do almost like the same good job. And there are all kinds of results that you could. I've mentioned some papers here, so if you are interested, you can go and look there for the more technical details and the kind of results that this kind of thinking allows us. So I would just conclude now by saying that there is a lot more that AI/ML offers here. There are applications across across the spectrum with respect to distributed generation, transmission and distribution. There are questions related to, for example, fault detection, reliability management, and using better equipment, discovery and synthesis of new equipment for transmission distribution. Then predictive analytics, for example, to let users know where they are using most of their their energy, and if there could be certain incentives to shift their demand peaks. Essentially, theft detection can be done. There is also dynamic pricing that can be done. So all kinds of things can be tackled very naturally with help of AI. I would also mention that quantum AI is becoming increasingly relevant, and I believe should be leveraged, because many of these energy related problems, they require optimization over a large combinatorial space. For example, when you talk of the possibilities that you have to prune, or the search space that you have to navigate. So this synergy between AI and quantum holds a lot of promise, and like we've just begun, but hopefully there are tons of things that that can be done in this space. Yeah, I'm happy to take any questions if there are.